Evaluation problem. Given an observation sequence O equals to O1, O2, O3 until OT, and a state sequence Q equals to Q1, Q2, Q3 until QT, the probability of observing O given the state sequence Q is simply the probability of O conditioning on Q and lambda equals to pi, where pi with index t starting from 1 to t of the multiplication of such a term. The probability of OT conditioning on QT lambda, which is equals to BQ1 of O1 times BQ2 of O2, and so on times BQT of OT, which we cannot calculate because we do not know the state sequence. The probability of the state sequence Q is the probability of Q conditioning on lambda equals to P of Q1 times the pi with index t starting from 2 to capital T of the multiplication of the term. The probability of Qt conditioning on Qt minus 1 is like the Markov, which is equals to pi q1 times a q1 q2 times a q2 q3 and so on times a qt minus 1 qt. Then the joint probability is p of oq conditioning on lambda equals to p of q1 times pi with index t starting from 2 to capital T of p of qt conditioning on qt minus 1, then times pi with index t, this time t starting from 1 to capital T of p of qt conditioning on capital OT conditioning on qt. That is pi a1 pi q1 times b q1 of O1 times a q1 q2 times b q2 of O2 times a q2 q3 and so on times a qt minus 1 qt times b qt of OT. We can compute p of O conditioning on lambda by marginalizing over the joint, namely by summing up over all possible q, that is p of O conditioning on lambda equals to sigma summing for all possible q of p of O q conditioning on lambda. However, this is not practical since there are n to the t possible q, assuming that all the probabilities are non-zero. Fortunately, there is an efficient procedure to calculate the p of O conditional on lambda, which is called the forward-backward procedure. See figure 15.3. It is based on the idea of dividing the observation sequence into two parts. The first one starting from time 1 until time t, and the second one from time t plus 1 until capital T. We defined the forward variable alpha t of I as the probability of observing the partial sequence O1, O2, O3 until OT until time t and being instead as I at time t given the model lambda. Like alpha t of I equals to defined as the probability of O1, O2, O3 until OT and Qt equals to Si conditioning on lambda. The nice thing about this is that it can be calculated recursively by accumulating results on the way. That is, initialization alpha 1 of I equals to the probability of O1 Q1 equals to Si conditioning on lambda, and which is equals to, if we take out the definition of the conditional probability elevation, that will be the probability of O1 conditioning on Q1 equals to Si and lambda times the probability of Q1 equals to Si conditioning on lambda, which is equals to pi I times Bi of O1. Now recursion, see figure 15.3a, is alpha t plus 1 of j is defined as the probability of O1, O2, O3 until OT plus 1, and Qt plus 1 is equals to Sj conditioning on lambda as follows. By the division, we can expand that to the probability of O1, O2, O3 until OT plus 1 conditioning on Qt plus 1 equals to Sj and lambda times the probability of Qt plus 1 equals to Sj conditioning on lambda. It's like what we did during the last formula. And if we furtherly removing the variables of the second term and the third term, it will be the probability of O1, O2, O3 until OT conditioning on Qt plus 1 equals to Sj and lambda times the probability of OT plus 1 conditioning on Qt plus 1 equals to Sj lambda and times the probability of Qt plus 1 equals to Sj conditioning on lambda. So that will be equals to the probability of O1, O2, O3 until OT, QT plus 1 equals to Sj, conditioning on lambda, times the probability of OT plus 1, conditioning on QT plus 1 equals to Sj and lambda. If we expand the definition, that will also be the probability of OT plus 1 conditioning on QT plus 1 equals to Sj and lambda times sigma I summing for all P of O1, O2, O3 until OT, and QT equals to Si, QT plus 1 equals to Sj conditioning on lambda, which is equals to, if we keep the first term, the probability of OT plus 1 conditioning on QT plus 1 equals to Sj and lambda, and if we expand the term instead of the sigma, there will be sigma for all I of the term P of O1, O2, O3 until OT, and QT plus 1 equals to Sj conditioning on Qt equals to Si lambda times the probability of Qt equals to Si conditioning on lambda. This is by the equation. And if we keep expanding, that will be the probability of OT plus 1 conditioning on Qt plus 1 equals to Sj lambda, which is times the sigma I of the probability of O1, O2, O3 until OT, conditioning on Qt equals to Si and lambda as another parameter times the probability of Qt plus 1 equals to Sj, conditioning on Qt equals to Si and lambda, and times the probability of Qt equals to Si conditioning on lambda. So all of these three terms that has been calculated instead of the sigma, they all conditioning on the parameter lambda. And if we keep expanding, there will be the probability of OT plus 1 conditioning on Qt plus 1 equals to Sj lambda times sigma I of the probability of O1, O2, O3 until OT, and the Qt equals to Si conditional on lambda times the probability of Qt plus 1 equals to Sj conditioning on Qt equals to Si and lambda. So after several manipulation and also summarizing, that will be equals to the multiplication of two terms. The second term is Bj of OT plus 1. The first term is sigma summing for all I starting from 1 to capital N of the time alpha t of I times Bij. So this is very simplified. And alpha I of alpha t of I, the first term instead of a sigma, explains the first t observations and ends in state Si. We multiply this by the probability Aij to move to state Sj, and because there are n possible previous states, we need to sum up over all such possible previous Si, and Bj of Ot plus 1 then is the probability we generate the t plus first observation while in state Sj in time t plus 1. And when we calculated the forward variables, it is easy to calculate the probability of the observation sequence. That is P of O conditional on lambda equals to sigma, summing for all I starting from 1 to n, of the probability of O and Qt equals to Si conditional on lambda. That is equals to sigma, again, indexing for all I starting from 1 to n of alpha t of I, where alpha t of I is the probability of generating the full observation sequence and ending up in state Si. We need to sum up over all such possible final states. Now computing alpha t of I is a big O of n squared times t, and this solves our first evaluation problem in a reasonable amount of time. We do not need it now, but let us similarly define the backward variable beta t of I, which is the probability of beginning in Si at time t and observing the partial sequence Ot plus 1, Ot plus 2, and so on until Ot. That is the second part of our divisions of the sequence. Okay, now we define beta t of I equals to the probability of Ot plus 1, Ot plus 2, and so on until O capital T, conditioning on Qt equals to Si lambda. This can again be recursively computed as follows, this time going in a backward direction. Now initialization of this recursive function is that arbitrarily to be 1. That is, beta t of I is equals to 1. Okay, now the next step is the recursion. Beta t of I is equals to the probability of Ot plus 1, Ot plus 2, and so on until O capital T, conditioning on Qt equals to Si and lambda, which is equals to sigma summing for all j of the probability of Ot plus 1, Ot plus 2, and so on until O capital T, and qt plus 1 equals to sj, conditioning on qt equals to si and lambda. We keep expanding by removing the qt plus 1 equals to sj to the conditioning probability part. Then it becomes sigma summing for all j of the probability of ot plus 1, ot plus 2 until O capital T, conditioning on qt plus 1 equals to sj and qt equals to si lambda, times the probability of qt plus 1 equals to sj, conditioning on qt equals to si and lambda. That is equals to, again, sigma summing for all index j of the probability of ot plus 1. Now we remove all the states to the second term instead of the sigma. The first term now only has the probability of ot plus 1. Then conditioning on qt plus 1 equals to sj and qt equals to si lambda. This is a very simple conditional probability only between two states of the first two states of the sequence times the second term. Now we move all those big OT plus 2 and also until big OT here. The probability of big OT plus 2 and so on until big OT, conditioning on qt plus 1 equals to sj and qt equals to si lambda, times the probability of qt plus 1 equals to sj, conditioning on qt equals to si lambda. That is sigma j summing for all the probability of ot plus 1 conditioning on qt plus 1 equals to sj and lambda, times the probability of ot plus 2 and so on until big O capital T, conditioning on qt plus 1 equals to sj lambda, times the probability of qt plus 1 equals to sj, conditioning on qt equals to si lambda. So that is, in summary, if we manipulate and combine the terms, and by the definition, the sigma summing for all index j starting from 1 to n will combining all these three terms. The multiplications of aij times bj of big OT plus 1 times beta t plus 1 of j. And when in state Si, we can go to n possible next states Sj, each with a probability aij. While there, we generate the t plus first observation and a beta t plus 1, a beta t plus first of j explains all the observations after time t plus 1, continuing from there. One word of caution about implementation is necessary here. Now both alpha t and beta t values are calculated by multiplying small probabilities, and with long sequences we risk getting underflow. To avoid this, at each time step we normalize alpha t of I by multiplying it with ct equals to 1 divided by sigma summing for index j of the term alpha t of j. And we also normalize beta t of I by multiplying it with the same ct of the same ct. But here bt beta t of I do not sum to 1. We cannot use equation 15.17 after normalization. Instead, we will have, this is the results from Rabiner in 1989. The probability of O conditioning on lambda equals to 1 divided by pi t of the term ct. Or, if we take the log of this term, this formula, log of the probability of O conditioning on lambda is equals to minus sigma summing for OT of log of CT.